if you're really wondering how this translation and all will look like, so I thought I'll go down and show you some of those things. Okay, so if you see, right, if you do a nearest neighbor kind of interpolation, this is all target to source. Okay, this is all target to source. The first is Lena, but we have done a nearest neighbor kind of interpolation. So hopefully you can see the jaggedness, right, on the hat and other places. Whereas if you do a bilinear interpolation, it looks a lot more kind of right nice to the eyes. Gives you a more smoother feeling and gives you sort of a better feel. Then, then the next thing is a rotation. So this is a tower that I talked about, the Pisa tower. The answer is sitting there, so just ignore that. Okay. Well, it says 4 degrees, but maybe you can even do probably say better than that. So here is that rotation example, okay, which you are supposed to do. And if you notice, right, these zeros that are actually coming in here, this is simply because we are doing it as an implementation in the lab, right? But in a real situation, you won't get these zeros and all when you actually till some new information will come in. Okay, but since in this case there isn't anything outside of this mesh, so we simply include zeros there. Okay, it doesn't mean that in a real case, you get zeros and all. This is simply an implementational aspect. Then scaling, again, right, if you see here, this is like a zoom out, right? If you look at the second one relative to the first, it's like a zooming out. If you did an actual lab implementation, you will get zeros outside of this of Lena's face. Okay, here we have taken, my student implemented in a way that he knew what was outside this and he copied it. I was telling you yesterday, right? You could also do that if you had access to information outside of this, because in this case we knew what lay outside of the face, we could actually copy. But in reality, when you implement it, don't assume all that. Just so if you do this, if you zoom out, you will get zeros here. Okay, because you don't know what lies outside this grid. Okay. And then let's see what is next. Okay, now prior to going to the other things, I don't think there is anything. Okay, yeah. So, and in all of this, right, please kind of remember that when you do this target to source, okay, it doesn't mean that target intensities are known. Okay, the target to source, it simply means that we still want to go from a grid wherein we have no information. But the thing is, what you are trying to do is, instead of going from source to target, you are picking a coordinate here, which is a location that it's an integer location. You are applying the inverse transform, and then you are landing somewhere here in the source, for which you are using, let's say, the immediate 4 neighbors if you are doing a bilinear interpolation. And whatever is that intensity that you get by this weighted averaging, that intensity will get assigned here to this location, to the target. Okay. Starting from target to source, it doesn't mean that we know target intensities or something. No, in both cases we don't know the target grid. Target is the image, right, which we would like to arrive at. Okay, which is supposed to be generated given the source. So only information that we have is regarding the source. From the source we want to go to a target. Whether you go from source coordinates to target coordinates, or whether you come from target to source is what matters. And as I said, source to target is not really a good idea, so you go from target to source, so that you can actually visit every location in the target and come into the source, land wherever, and then use whatever interpolation that you are familiar with. In this case, I just showed you how you can do a bilinear interpolation, and you assign that intensity here, and then move on to the next location, do the same thing again, assign an intensity, and that is how you will fill up this. Right, that is how all those images have been filled up. Okay, now as I said, right, these are actually simple transformations, the one that we have seen, right, including in-plane rotation, in-plane translation, uniform scaling. These are all very, very simple examples. Okay. Now what I will do is I will write down, okay, what is called a hierarchy of this geometric transformations. Okay, there is a hierarchy of geometric transformations, and we will see from the simplest to the most complex one. Okay, and the idea is to know, actually, right, eventually it's like saying that from a moving camera, what do I see, right? If I see the world, right, all these geometric transformations and all, right, what they are trying to tell you is, if you had a camera, right, with which if you were to move, how would the world look like, right? So how will the world map onto your image? Now what you can show is, all these transformations and all you can do for simple cases. It doesn't mean that for every situation you can actually do this. Okay, you can, if you want to do that, then right, it may not be as simple as this. Not that it is impossible, because right, people do align whatever, right, any scene, any image of any scene to another image of the same scene and so on. But the goal, right, behind doing this kind of geometric transformation is to actually understand as to when you can do this, a simple one global linear transformation that can take you from one image to the other. That is a very elegant and special case, right? Because all that you have to do is get some matrix which you have to estimate, and then once that matrix is known, then you can simply, so that law holds for the entire image, correct? And that you can apply on that image to get to kind of say get the other one. Now this need not always happen, but whenever it happens, it's actually a very nice case. That is why whenever we talk about geometric transformations, there is something called a planar world. Okay, the planar world occupies a special place. Okay, even though we may not think of the planar world to be that interesting, for us, a 3D world is much more interesting. A planar is also in a sense, but then effectively, right, it is still a plane, right? So a planar world is what will be central to our argument. And right along the way, I'll also tell when you can actually relax this assumption. It's like saying that, so the whole goal is like this, right? I take a camera and I move. Okay, I want to know when I can relate the images across two views through a single linear transformation. Okay, that is the goal. Now, whether you can do, can the scene be completely arbitrary, in the sense that suppose I take this classroom where, let's say, it's a complete 3D world, and I take a camera and translate. If I take an image from here, I take an image. Is it true that I can relate the two? The answer is no. But if I were to stay right there and if I simply rotate the image without translating the camera, can I actually? So it's like saying that I take one image like this and then I rotate about the center of the camera without translating the camera. If I take another image, can I relate? The answer is yes. Okay, so we want to know as to what is that, right? What is it that? So the whole idea is taking a camera and moving, and then trying to relate images that you capture along the way. When can you relate them, and when can you relate them in a straightforward manner? By straightforward manner, I mean one transformation, one linear transformation that will take all the pixels here to the other grid. Each pixel can move in its own way. That is all right. We are not saying that they should all move by the same amount. For example, if you do a simple rotation, right? Rotation, as you understand, about the origin, that pixel never moves actually. Whereas as you go outward, radially outward, the guys at the boundary actually move a lot. The guys that are closer to the origin don't move at all. In fact, the guy at the origin doesn't move at all. Right? All that is okay. We don't mind, right? Each one moving by its own account. But there should be one transformation that should take them all. Okay? We don't want, for example, one transformation for this part of the scene, another transformation for that part of the scene. Right? That we do not want. We want just one transformation that will take us from here to there. Doesn't mean that pixels will all move by the same amount. No. If it's a translation, maybe yes, but if it's a rotation, it doesn't happen. Scaling, it's not true, right? Different pixels move differently depending upon where they are in the image. Okay, so the goal is to sort of arrive, actually we want to get off, in our head, we want to be able to think about what camera motion and what scene will lead to these kind of transformations. For example, you can ask, when I said yesterday that you can simply get a translation, like, what is that, some TX, TY, you might want to know when does that happen. Can I simply take a camera, translate here, take two images and claim that these two images will be related by a simple shift of TX and TY for all the pixels? Okay, things like that. Right? Or for example, can you have a plane that is inclined and this camera is looking at it, then what happens? Does it have to be fronto-parallel? Can that be inclined? Right? In what situations, what will happen is what we want to see. Okay, so but I thought initially, right, so the reason was we'll start with a very simple case where we won't really worry about what was the camera motion, what was the scene and all. We simply say, right, this is the transformation that works. But now we want to step back now, and we want to analyze as to what motion and what scene will lead to what transformation. And again, the transformations are not limited to the three that we saw yesterday. There's an entire hierarchy. Okay, you got this? All right, so we will kind of go through. So that I just want to set the tone for why we are doing this. Okay. All right, so this hierarchy, right, the simplest is what you saw yesterday. Okay, so the first one is what I will call as, okay, so here, right, what you have is this xt, yt is equal to, okay, this is xt, yt is equal to xs ys plus tx ty. Okay, this was the one that we saw yesterday. This is one of the simplest. And what kind of things, right, will it kind of keep intact in terms of the image features? Angles and lengths are kept intact, are preserved, okay, or they kind of say remain intact. So that means your angles don't change. So what this means is that if you had let's say a square like that, and if you applied a transformation, it will remain a square, except that it would have just shifted, right? None of these angles change, these remain as right angles, then they remain as right angles, the lengths don't change, nothing happens. The next one is actually a rotation, which is xt, and all of this is all in the image plane. Okay, this is all motion in the image plane. Tx ty is all on the image plane, right? When we down the line, we will see when the camera motion enters into the picture. Xt yt is equal to cos theta sin theta, if you are looking at a clockwise rotation, minus sin theta cos theta, and then xs ys. Okay, this is what we call as in plane translation. Last time itself I wrote down in plane. This is also in plane rotation. And what does it keep? Angles are actually preserved. And of course, the angles as well as lengths are preserved, right? So that is common to both, in fact. So you have this, then you might actually end up seeing something like that, right? Or this is a right angle, so is this, and so on. Okay, those angles and lengths are kind of preserved. Then let's look at uniform scaling, which is xt yt, and I got to deliberately tell uniform. Okay, so here I'm going to use a0 0 a, and then I have xt yt. Okay, this is uniform scaling. Xs ys, sorry, xs ys. This is uniform scaling. Okay, and here angles are preserved, and ratios of lengths are preserved. Ratios of lengths are actually preserved. So the idea is, what do these kind of transformations do to your image, right? So that is what we are interested in. Then up the hierarchy, right? The next one that comes up is xt yt is equal to, let's say, scale, which is actually uniform scaling. Okay, if I call this as S, this is uniform scaling. Then rotation, this is in plane rotation, R, and then you have your xs ys plus tx ty. So if you look at the number of unknowns, right, as you are going, so here you have 2, here you have only one unknown, here you have one unknown, but in the case of similarity transformation, you will have one unknown coming up here, 1 plus 1 2 plus 2 4. So you got like 4 unknowns, and this is called a similarity transform. And a special case of this are your uniform scaling and all of that, right? When let's say something is from R is identity, and you have only scaling tx ty 0, then you get uniform scaling. So you can derive the previous 3 as special cases of similarity transform. So this is similarity transformation. Okay, this is called, and it has 4 unknowns. So these unknowns are the ones for which, when you need to solve, you need those feature point correspondences and all that. And here's what it says is angles and ratios of not necessarily parallel segments, not necessarily parallel lengths, or not necessarily parallel lengths are preserved. So if I want to draw some kind of a diagram, right, what it might mean is, if I want to indicate something like this, okay, then there could be a rotation and so on, but well, right, I mean, I don't know whether I'm drawing it exactly, but something like this is okay. So even though, right, these two segments are not parallel, okay, it doesn't matter. as long as there is uniform scaling, right? So that is what is special about discriminatory transform. Involves a uniform scaling, involves rotation in plane, and then a translation is again in plane, right? So 4 unknowns. So what it can do is it can actually keep these things intact. You can go above that. What's called an affine. Okay, the next one up the hierarchy, right, is what's called an affine transformation, and that will look somewhat like this. So you have xt yt is equal to abcd. Okay, some abcd, then xs ys plus txty. This is what is called affine, and most of the time, right, this seems to be the one that, let's say, people think usually happens, but of course, there's something else about this that can also happen, but affine is very, very common. What it can do, parallel lines remain parallel, which means that, okay, let me finish this. Parallel lines remain parallel, angles are not preserved. So so what it can do is it can take something like this and do something like that. So parallel lines remain parallel, but then the angles can change. If this was right angle, this need not be a right angle anymore. Angles are not preserved. It preserves. Actually, what it does is it preserves what is called a cross ratio. Preserves ratios of lengths of the parallel segments. Okay, preserves. Okay, but then of course, right before that, let me write this. Preserves the ratios of lengths. See, earlier case, right, what I had written was it will actually preserve ratios of lengths of not necessarily parallel. Here, this will preserve ratios of lengths of the parallel segments. The earlier one, if you see there will be a small difference. There I had said, right, not necessarily parallel. Here, if you have an affine transformation, then the angles can change, but then what it will do is parallel lines remain parallel. If you go higher than this, right, there is something else that can happen. Okay, but then that involves what is called a full camera motion. Okay, these are all, see, whatever we have seen till now is all kind of a restricted camera motion. When you have a full camera motion, what does that mean? That means, we call it a 6D motion. A 6D motion, by which we mean you can have 3 translations, involves 3 translations along x, y, and z axis, and 3 rotations about x, y, and z axis. Okay, which is so, right, this is the most general form. And in order to even write this kind of a mapping between the source and kind of a target, we have to actually go to a different sort of a coordinate system. Okay, I'll talk about it now. Okay, so basically, this is the most general form. This is called really a projective transformation. This is called a projective it has a name. The other one was affine. This is called a projective transformation. And this is the most general form, okay, in which you can relate, right, images of a scene where the camera can undergo arbitrary motion, okay, arbitrary 6D. Okay, now what does it kind of say retain? So lines remain lines, thankfully. Okay, parallelism not preserved. Whereas in affine, right, you had that parallel lines remain parallel. Here, parallelism not actually preserved. Lines remain as lines. Well, it is supposed to preserve what's called a cross ratio. Okay, anyway, right, we don't, all that is effectively means is that the right midpoint of the segments and all, they don't change. The midpoint remains where it is. Okay, we don't have to get too much involved into those aspects. But just remember that You might ask, I mean, right, can it ever happen that a line could change or something, right? You use a camera. Have you ever seen that, something like an edge becomes a curve or something? Because I said lines remain lines. I mean, I mean, why the hell would a line turn into a curve or something? Have you ever seen that happen? Or can you think of situations when a line can become actually bent or something? Yeah, so right, rolling shutter is one such example where it can happen, right, where it happens because of the camera motion. Right? You see, there are other cases when if you notice spherical aberrations and all, right, those are lens aberrations. We are talking about when does camera motion lead to something like that, a line or something becoming bent, right? So you can imagine that, if you were to take a camera and suppose you move, and suppose this is not your usual camera, it's like a rolling shutter camera. In fact, you should actually check this out. It's not so hard. Take your cell phone, and then you kind of look at the edge of a wall, and then you go like this fast. Okay, go like this and come back. Okay, so what will happen is if your motion is fast enough, then what happens is, because all sensors are not exposed at the same time, so what will happen is the top few rows would have observed this motion, okay, which means that the line will kind of tend to bend this way, and then because you're coming back and forth, you're coming back, so then the rest of the portion will try to bend inwards, and if you see that image, right, that will have some kind of a curve, which actually means that it is introducing something that is actually not in the scene. Okay, that could complicate matters. On top of that, you may have blurring and all that, but then blurring never changes the line into a curve. Blur will only smear a line, right? If you have seen, if you blur a sharp line, what will happen is it will smear around it. It won't become bent. Okay, so rolling shutter is a very, very special case. Okay, but then of course because most cameras have it, so it's kind of it is also important to know. Now one more thing that I forgot is there's something called shear. Okay, there is a special case of affine. Okay, which is called the shear. Okay, let me write that down here. Okay, what is called a shear? It's actually a special case of affine. See, ABCD is affine, right? Now, a special case is something like this. What we call is, X shear. So, this will look like 1K 01 XS YS. So, what this means is that your XT, it will be like XS plus K times YS, and YT will remain equal to YS. Okay, this is called a shear. So you see, right, this is a special case of that ABCD. K can be 1, K can be greater than 0, it can also be positive, negative, whatever. Okay, if K is 0, of course, then in that case it's not interesting. And this will kind of, right, so this is in fact called an X shear. So what it will do is, it will take your guy like this, and it will do this. So your Y, so if you see, right, your X changes. If you think of this as 0, 0, whatever, right, 0, 1, 1, 0, 1, 1, you try to plot it, then what will happen is your Y coordinate, you see, Y hasn't changed, right? This is at, let's say this height is 1, so this is also at 1. So all these coordinates, the Y coordinate will be 1. The Y coordinate for this entire segment will be 0, but the X coordinate will change depending upon what is the Y, whatever is the Y coordinate. For 0, 0 will stay there. Then for, let's say, 0, 1, it will move. X will move like 0 plus whatever. If K is 1, it will be like 1 times 1. So it will become 1, right? So this point will go here, this point will go there, this point is here, and this point is here. These two don't move because Y is 0, right, for those 2 points, correct? So this is called an X shear. I don't know, this is something that you actually experience, right? Think of something like, you move inside a car, right? You're traveling by car, and assume that assume that on the road, right, if you had Y camera, if you just look out, right, you're not the driver, hopefully you don't want to be looking out of the window and driving, right? Assume that you have somebody who's driving the car is going this way, and you look out of the window, and suppose you saw a zebra crossing on the road, okay, and suppose this car is translating this way, then the zebra crossing will get sheared. In your eyes you can see that shearing effect. Or you just take a camera and if you capture it, next time when you travel, do that, right? Watch out for that zebra crossing, right? And you take that picture, not the driver, right? So that is what, and then you can also have a Y shear, right, which is like 10K1. So this is called shear. This is a special case, and all of this, right, I want to come back later to be able to, we should be able to answer as to when these things happen, right? Now I'm just writing down some matrices and saying that, right, this is shear, this is that. But ideally you will get a nicer insight, a better insight if you were to now visualize what camera motion and what scene will cause this matrix to occur. Okay, any doubts at this point? This seems to be problematic. Now, what I'm going to do is, I'm going to look at a projective transformation, because that is the most general, and then everything else will be a spin-off of that, right? Once you understand how you can arrive at really a projective transformation, it has actually 8 unknowns, by the way. Affine will have 6: A, B, C, D, T, X, T, Y. I didn't write that. Let me write it down. I think I forgot. Okay, so where is that affine thing? Here. So it has 6 unknowns. So all these unknowns are things that we might have to solve for, right? Because nobody will tell us what is that A, B, C, D. They may just give you 2 images and they'll say, oh, align them. Then we should find out what is this A, B, C, D and T, X and T, Y. This projective transformation has 8 unknowns. Okay, we will see why down the line. Okay, and that's the most general form.